Yes,
So did Logan just give up on this class or something?
he dropped this class, so
Yeah.
yes. Yeah, I'll talk about that in a second. Okay, so polarizability means how easy it is to make a dipole. It increases with more electrons. It really means how easy it is to get the charges imbalanced on one side or the other. So if you have more kids, it's way harder to keep track of them, right? If you're just helium or hydrogen, they they have these forces, but they're super weak. The bigger you get, the more electrons you have, the easier it is to be polarized or become out of balance. Does that make sense? Okay. Then it's also the same reason, really, why a straight chain one, all right, and it lines up with another one, whatever. I don't know, those were supposed to all be next to each other, but whatever. If these come into contact with each other, it's easier for these to be, pushed away or attracted, whichever way you wanted to draw it, than it is like when you just have a blob and the electrons are already in atoms that are kind of going that way and that way and that way and that way themselves anyway. So polarizability, the larger and really straighter or less complex, the greater. Um, all right, then pi bonds.
Why is it called a pi bond?
I don't know. That's a great question. Pi bond, we have greater overlap, so we have more electron-electron interaction. So the theory is it's easier when they overlap this way to get an imbalance again. So you'd end up with all of them on one side and all the nuclei on the other side, essentially, versus sigma, where it's just end-to-end overlap, and they really don't interact as much, so they're less likely to be out of balance. And this one's not usually tested, but it is important. Okay, so London dispersion forces, they exist between every single thing that we have. I think I'm on the wrong slide. There we go. Okay, so we have ion. Whoops. That's when something ionic dissolves in something polar. We have dipole dipole. That's when we have two polar things, which once again, they could be the same two polar things. London dispersion forces, the most complicated to explain, but it's when we have induced dipoles that are momentary. All right. So they get out of balance. There's a little attraction, but then they're right back to balance and the attraction's over. But if you have this happening thousands and thousands and thousands of times per second, then there will be an attraction. Not as great as the rest, but there will be an attraction. John. Yeah. Yeah, that's a good way to put it. You like those? So here we got Cooper, and we have which one of his six girls should we name right now?
Tegan.
No, we won't. All right, make sure you understand. London dispersion forces are in everything. Okay, then finally, hydrogen bonding. Hydrogen bonding is discussed in biology. It was discussed earlier in this class. Go ahead, Judah. Oh, that's fine. It means everything. Yeah, it's in every single thing. It's in anything that has electrons. So, which is everything.
And what's hydrogen? Yeah. Not H plus.
All
That's
right.
the only thing that we
So
know.
here we go. Hydrogen bonding is a very strong form of dipole-dipole bonding. You should know that hydrogen is really a form of dipole-dipole. Hydrogen bonding exists, and I think we said this right at the end of yesterday. Just NOF, or just remember, hydrogen bonding is fun. Yay. All right. Right. Now, yes. Yeah, yeah. So it works with NO and F, and that's because the difference in electronegativity, really. All right. If we have H and N, I don't know what it is. H and O, I do know that one. H and F, I know that one. The difference here is it's there, we're back. We're back. That's 1.0. This one's 1.9. I don't remember this one, but it's around 1 again. The electronegativities for these three are high enough that you have a dipole created. I don't usually draw it this way. It's upside down, but whatever. That is enough to pull the electron really far enough so that the hydrogen really is kind of just an exposed nucleus. And then I don't know why I did that. That's supposed to be a negative sign. Sorry. It's because I wrote it upside down. All right. So when we have these three things, it's enough to pull and create a dipole strong enough that now hydrogen can form what's called hydrogen bonding. Yeah, and we talked about that in chapter 9. So we have CCl4. I don't know why that was so hard for me. Right. And one of them back here. They all pull, but all the dipoles cancel out. So even though this bond is polar, the overall molecule will be nonpolar. So and you would be expected, they could ask you what type of intermolecular forces are in carbon tetrachloride, and you would only say London dispersion forces. It'd be tricky because you're like, oh, it's C and Cl. That's dipole dipole. You would be wrong. So we do need to remember what we learned in chapter 9, and that is that the structure can affect the polarity, not just the imbalance. The other thing that has to happen for hydrogen bonding is hydrogen bonding isn't technically attracted to oxygen. We say it is, but it's attracted to the non-bonding pairs of electrons. So let me draw this the right way. You may remember there's two pairs of electrons up here, right? So we always say the water molecules, the hydrogen bonding is the hydrogen is attracted to the oxygen. That's sort of not true. It's attracted to the non-bonding pair of electrons. So we would always have to have a non-bonding pair present as well. Yes. So this thing is super strong, and that's a covalent bond. This attraction exists, but comparatively, it's extremely weak. Here's my example. We probably played with these before, and I don't have hardly any of them left because people steal them. But here are some water molecules. They are cool. So we've never seen them? Okay, my bad. So this is a water molecule. And the OH bond is like how this is snapped together. Like that's a bond. That's a covalent bond. The hydrogen bond is just how these two magnets sort of stick. So it's kind of there, but nowhere even remotely close to trying to pry that off. That kind of makes sense? So now, if there is an attraction though, and I think about states of matter, if I'm going to turn the water into a gas, okay, so I need these all separate. It takes a little bit of energy. Let me get that lined up right. It takes a little bit of energy to pull each one of them off. Okay, but if they, whoops, there we go. So it does take it. Nisha, pull on that. How hard is that? Not hard, but does it exist?
Yes.
Yeah. And these things we're talking about this entire chapter, they're just like magnets sticking together, but not how the magnets are stuck, like the bonds in the middle of them. Does that make sense?
Is that how like it's always rearranging?
Oh, hold on, Nisha.
Is that just why it's something like a liquid stuff that's always rearranging because they're not super strong?
Yeah, they're not strong, and they can. A liquid technically. So the liquid of these water molecules, they can just move around. And water's unique, we know, because its density is lower as a solid, right? So you can see it. It's because of hydrogen bonding. You can see it right here. See that hole right there? That would have nothing or air in it. But if this was liquid water, they wouldn't be rigid, and then those gaps wouldn't be there. That's why ice expands. If I shake this, it made its own little gaps. Here, you can play with them, but don't get lost. Okay, sorry. What?
That's why you can't put like an open bottle of like soda or anything in the freezer that has water.
Right, it expands, and if it's not a good container, it'll burst. Okay, you guys asked me something and I ignored you. Shh, go ahead, Judah.
It's just something small. Like, it doesn't require a lot of force, but there is force there.
Right, that's why I have to heat ice to make it melt. That's why I have to add heat to make it boil. Right? Now, I can heat water a ton, and it's not going to break the O and hydrogen, like the covalent bond, that's not going to break. That would be an intra versus an inter.
How would you, like, if something has a boiling and a melting point, how do you get to the each? If like the melting point is higher than the boiling point, would it not boil first?
That doesn't exist. Well, it does for carbon dioxide. And we don't call it that. We call it sublimation.
So it's either one or the other.
And we'll learn about that actually, not today, but in the next 36 hours. Okay. I meant to say, what's today?
The 21st.
Thursday. Not having school Mondays really screwed me up. All right. Here we go. Shh. This part right here cannot be understated. You will have to do this on your test. To determine what type of IMF is dominant, check the type of bonds involved. If there is an ionic and a polar substance, the IMF, or the most important intermolecular force, would be the ion dipole. If it's polar, it will be dipole-dipole. If there are only polar substances, or sorry, non, that was by the arrow, it will be dispersion forces. So it will be like salt water. We already talked about this yesterday. It would be like gasoline or octane. And then it'd be like NH3, ammonia. Sure. Okay, so salt water, if we were asked all of them, every single one of these, I would say LDF.
And then hydrogen bonding with an H3, right?
All right. I can put hydrogen bonding.
What's the middle one?
Octane, that's just C8H18. It's gasoline. It's what we put in our cars. All right, let's stick with NH3. Anything else?
Dipole-dipole.
Dipole-dipole. NH3 is polar. So dipole-dipole. Is there any ion dipole? No, because there's nothing ionic present. Okay. Octane, only C8H18. So I only have London dispersion forces. Okay.
Would that be the case with all carbohydrates?
I would say every single carbohydrate, because some carbohydrates are not just C, H, and O's. They do have some of their functional groups, but most. If you don't say carbohydrates, but if you say alkanes, I'll say yes. All right. Now, let me ask you a question. Who's ever used a barbecue before? Okay. Most of those burn what gas? Propane, which is a gas at room temperature, right? It's C3H8. Could you explain to the person next to you why what we cook on a barbecue is a gas at room temperature versus what we put in our car, which is a liquid at room temperature? Why, even though they're the same type of things? They're just C's and H's. You want to tell me, Grace? So I'm going to use Grace. Are you okay with that, Grace? Grace gave me a 3-point answer, but I want a 5-point answer, so we discussed it. And she knew it, she just didn't put enough detail. So at first she said, because octane has greater intermolecular forces. And that is a true statement, but that'd be 3 points out of 5. So I said, be more specific. And then she said it had greater London dispersion forces. That's better. But I want one more slice to that pie. Oh, wow. John, I want you to be right, so I'll go to you.
Okay. So I said kind of the same thing Grace did, but I noticed that the gas, like the octane part, it was a bigger molecule than the propane.
Okay.
So that increases the contact area and the molecule size, which are both things from the video.
Good. And that's probably what both of you were going to say also. Octane has greater London dispersion forces because it is a larger molecule. Larger molecules, higher London dispersion forces, higher London dispersion forces, the higher the boiling point, whatever. We don't have to write all that, but just over and over. Go ahead.
So London dispersion forces are why gases can, there's like, I guess like O2 and 2.
Yep. We need to do one of two things or both. Got to get them cold or put them under a lot of pressure or both. And think about what cold really does and what pressure really does. It makes them get close enough.
Well, no, I mean like gases like dissolve in
Oh,
water.
I didn't hear that part. Say it again then. I'm sorry.
Like gases like O2, like that are dissolve.
Yeah, they mix into the water. And that's because they still have some attractive forces to that water, not necessarily dipole, but yeah, that's why they'll mix up. Okay. All right. All right, salt water. Remember, because this is on here a ton. It's all of them. It's all of them. Ion dipole, dipole, London dispersion, and hydrogen bonding. It would have all of them. Interesting. Okay. So far, so okay?
So the ionic,
Ion dipole?
and the hydrogen bonding, they both come from the Na. No, not the Na. The ion comes from the Na bonding the, not bonding, but I don't know what I'm saying.
It comes from the Na plus.
Na plus not bonding, but like
being attracted to the O, which is yes, I think. And then you're going to say hydrogen of the other water. It's because the H is sort of attracted to the O.
Yes.
Yes, they're very similar reasons. I believe Cooper just made a. Okay.
I don't think that's good for someone with ADHD.
It's not ADHD, it's
All right.
That's different.
Look at these questions. Shh. We were supposed to be here, and we just got here. So I want you to look at these two questions right here. Let me make this one bigger. That's a little better. Okay, Tom. Here we go. Now, number 3 we haven't talked about, but I feel like you could figure that out. Number 3 has nothing to do with this, by the way. That's the options to the previous question. Oh man, how did time go by so fast? What would you say here? Sorry, what would you say here? I'm sorry, my mouse went here. It's this one. Because heat of vaporization is when we turn a liquid to a gas. So the energy here. Okay, which of the following has the lowest boiling point? HCl. That's your guess. That is not the right answer. It's not H2O. It's SiH4 if I remember. I'll have to look it up. Oh, actually no, it's H2S. This is it. For sure. No argument.
Is it because it's a gas at room temperature?
It is a gas at room temperature. It's less polar. It has no hydrogen bonding. And it's smaller. Sorry, that was. You're welcome.